The overarching mission of our project has been to develop a non-degradative method for recycling solo cups into thread.
The process begins either with solo cups or with mixed shredded recyclate that includes shredded solo cups. Both are dissolved in D-limonene, which is a natural solvent highly selective towards polystyrene, and then filtered. The resultant pure polystyrene D-limonene solution is then reprecipitated, either using steam distillation or a heptane bath. Within the heptane bath, we can either perform bulk precipitation or wet spin the polystyrene out using a syringe pump. Either of the bulk methods can be turned into dog bones from tensile testing, and all three can optionally be combined with other polymers for improved mechanical properties for fabric.
We ran tensile tests on both our recovered polystyrene dog bones and 4 different blends of polystyrene. For the recovered polystyrene dog bones, we found that the steam distillation was the least successful method since not enough D-limonene was extracted from the polystyrene. You can see the blue line of the top graph displays an elastomeric curve atypical of polystyrene. The heptane dog bone that went through the most heptane washes and longest drying time had mechanical values closest to that of polystyrene literature, indicating the best recovery. All 4 of our blends displayed mechanical property values within the range of polyester, a very popular synthetic fiber, indicating the possibility of success of these blends in fabric. At the bottom, you'll see 3 optical microscopy images of our precipitated filament polystyrene. We found that a 20 weight% solution injected at 0.05 milliliters per minute with an 18 gauge needle produced the smoothest and most uniform filament.
In the rightmost image in the optical section, you can see that we've produced filaments of different colors. We found that the longer the thread spends in the heptane, the lighter in color it becomes as more dye is leached from it. We believe that this is correlated to the D-limonene leaching as well, as the lighter threads were stronger and firmer than the more vibrant ones. A side benefit of this is that the lighter threads were easier to dye over with whatever color you may desire. Finally, we performed AFM on our blends. As you can see, both blends take the form of one polymer forming the bulk matrix and the other forming small discrete precipitations, which is to be expected for compatibilized blends and indicates their success. In conclusion, we believe that our work has been highly successful. Our ability to non-manually separate and clean polystyrene and then reprecipitate it is very promising. Additionally, similar processes have been performed commercially, indicating the ability to scale our process as well.
Future work could entail stretching of the filament during heptane injection to produce molecular chain alignment and a stronger filament. Another possibility is the separation of the heptane, D-limonene, and dye solution, potentially via distillation, in order to reuse the components. We'd like to give a shout out to our team members Tina and Jason and our mentors Lauren and Dr. Wilson, without which this project would not be possible.
And finally, a huge thanks to Professor McGuigan, Phil Chapman, Steve Farias, Ellen LeBau, Shania Poston, Yi Jung Hu, and Professor Mao for all of their help.